Hi everybody. Mechatronics systems can often be split up in so-called basic systems. This video is the first one in a series of three which discusses these basic systems, and in this video we are going to look into first order systems. First order systems can be divided in four groups. We have a so-called integrator, differentiator, a bias integrator, often called the first order system, and the bias differentiator. Let's start off with looking to the integrator. Well, when we have a integrator and we want to derive the mathematical model in a time domain, we get the output signal y equals the integral of the input signal x. So y is equal to the integral of x, so the integral of x dt in a mathematical form. We've seen that by replacing ddt by s in the s domain is a way of getting rid of that differential equation and go to the Laplace domain. So when ddt equals s, then the integral can be replaced in the s domain by 1 over s. So in the s domain it becomes y equals x times 1 over s. So y is equal to x, the input signal, divided by s. So that is the representation of my integrator in the s domain. Then we can also define the transfer function. And the transfer function h is equal to y, the output, over the input x. So y divided by x, which is equal to h, the transfer function is equal to 1 over s. In the j omega domain, we can replace s directly by j omega when we are looking only to harmonic signals. And then we get y equals x divided by j omega, or y equals 1 over j omega times x. So the transfer function in the j omega domain and the frequency domain equals h is 1 over j omega. Again, that s is replaced by j omega here. When we analyze a system in the j omega domain and frequency domain, we often look to the Bode plot. And in the Bode plot, we look to the amplitude and to the phase. Well, the amplitude of this system, the integrator, is equal to the amplitude of the numerator divided by the amplitude of the denominator. Well, the amplitude of the numerator is 1, and the amplitude of the denominator is the real part squared, 0, plus the imaginary part squared, which is omega squared, and then the root taken out of that summation, so that equals 0 plus omega squared, and the root out of it, so that it's equal to 1 over omega, which of course can also be seen directly over here. So when we are looking to the Bode plot, the Bode amplitude plot, we're not only drawing directly the amplitude, but we are taking the logarithmic function of the amplitude and multiply it by 20. So the amplitude for the Bode plot is equal to 20 times the log of 1 over omega, which is equal to minus 20 times the log of omega. The phase of omega is the phase of the numerator minus the phase of the denominator. Well, the phase of the numerator is 0 because this is a real number, and the phase of the denominator is always 90 degrees because that's an imaginary number. You can also say in the denominator it's a minus the arctangent of the imaginary part omega divided by the real part, which is 0 in this case, so it's minus the arctangent of a really huge number, which equals minus 90 degrees for all frequencies. So now let's look to a couple of specific frequencies. We are looking to omega is 0. We are going to look to omega, which is infinite, and we are looking to the so-called crossover or cutoff frequency. And in that crossover frequency for that integrator, we look to the value of omega where the amplitude equals 1. So 1 over omega equals 1, so we are looking to the frequency of omega is 1. So for omega is 0, the amplitude is 1 over 0, which is an infinite number, and also 20 times the log of 1 over omega, or minus 20 times the log of omega equals an infinite number. For values of omega which are infinite, we get an amplitude which is 1 over an infinite large number, so it's 0, and 20 times the log of a really high number with a minus in front of it equals a minus infinite number for the amplitude. At the crossover frequency omega is 1, we get an amplitude of 1 over 1, and in the logarithmic function we get 20 times the log of 1, which is 0, so we get 0 dB over here. And we have seen that the phase for all frequencies is minus 90 degrees. So with that information, we can draw the Bode amplitude and the Bode phase plot. So the Bode amplitude plot looks like this. We have seen that the omega, when the omega increases from 0 to infinite, we see that the amplitude decreases from an infinite value to a minus infinite value. And at the crossover frequency, we get an amplitude of 1, or in dBs 0 dB. We can also see from this expression that when omega increases with a factor of 10, then my amplitude decreases with minus 20 dB. For instance, when omega is 1, then we get the log of 1, which is 0, so we get 0 dB. And when omega is 10 times higher, which we call a decade, then we get the log of 10, which is 1, so then it equals minus 20 dB. And that's why this first order system drops with minus 20 dB per decade. And here at the crossover frequency of 1 over Ti in this example, because in this example my transfer function is 1 over j omega times Ti, my amplitude is 0 dB. And we have seen that the frequencies for that the phase for all frequencies is minus 90 degrees. We can also draw the Nyquist plot, and then we look again to this transfer function over here, and we see that the phase is always minus 90 degrees for all omega values. So we have a Nyquist plot which is always on the minus 90 degrees imaginary axis, so the negative imaginary axis, because this is minus 90 degrees, so it's always on the negative imaginary axis, which can also be seen directly from this transfer function. And we see that when omega increases, the amplitude decreases. So that's why the Nyquist plot starts for very low frequencies over here, and on the real negative imaginary axis, the amplitude decreases as the omega increases. And finally, we get into the origin. We can create an integrator by making it, for instance, in this way with an op amp and an R and a C. And in the Laplace domain, we have a transfer function which is equal to h is 1 over s times ti. By looking to this function, we can look to the poles and the zeros of this function. We see that there is no expression with an s in the numerator, so that means that there is no zero. And we see that there is one term with an s in the denominator, which means that there is only one pole. And that pole can be calculated by setting this denominator to 0. So we set s times ti to 0, which yields a pole which is equal to s is 0, or a pole in the origin. So this is typical for an integrator. When you see that you have a system pole in the origin, then you have an integrator in your system. And of course, examples for integrator, not only in an electrical way, are also in a mechatronic way. For instance, when we go from speed to position, or in other ways in which we integrate, for instance, accelerations to speed, etc. So integrators are very often in your mechatronic system. Then we are going to look to the differentiator. And the differentiator says that the output is the derivative of the input. So y equals the derivative of x, so it equals dx dt. We can go directly to the S domain by replacing d dt by s, and then we have y equals s times x. So my transfer function y over x, which is defined as h, is equal to y over x is s. And in the j omega domain, we can replace s by j omega, and then we get the transfer function h is equal to j omega. And of course, we have the expression over here, y equals s replaced by j omega times x. Well, the transfer function I said is h is j times omega. So the absolute value or the amplitude is the absolute value of this expression, which is equal to omega. You can calculate it also by taking the square root of the real part squared, which is 0 squared, plus the omega squared, which yields omega. The phase is equal to 90 degrees because this is a complex number with only an imaginary part. So this always is in a Nyquist plot, for instance, a number which is up on the imaginary axis. You can also calculate it by taking the arctangent of the imaginary part, omega, divided by the real part, which is 0. So it's the arctangent of an infinite number, which goes to 90 degrees. And for the Bode plot, we've seen that we are taking 20 times the log of the absolute value over here. So 20 times the log of omega. Well, we now can look into specific numbers again. We look to omega as 0, omega as infinite, and omega which is equal to the crossover frequency, or in this case, the frequency in which the amplitude is equal to 1. So when omega equals, which is transfer function, equals 1, then omega is 1. So at omega is 0, my amplitude is 0, and 20 times the log of 0 equals minus infinite, an infinite number. At omega is 1, my amplitude is 20 times the log of 1, and log of 1 is 0, so it's 0 dB. And at an infinite number, we get an infinite number over here. And we have seen that for all frequencies, the phase is 90 degrees, which is the opposite phase of an integrator. So looking to the Bode plot, the Bode amplitude plot, and the Bode phase plot, we see that we started off with an infinite number and we end up with an infinite number. And exactly on the crossover frequency, which can be calculated when we have in this expression h is j omega times ti. So we can say, well, the crossover frequency is equal to the inverse of ti, so 1 over ti, and at that frequency my amplitude is 1, or it's equal to 0 dB. And when we go back to this expression, we see that when omega increases with a factor of 10, then this expression, so 20 times the log of my amplitude, increases with 20 dB. So we say for a differentiator, we see that the amplitude increases with 20 dB per decade. And a decade is an increase in frequency with a factor of 10. So we get a line like this, which increases with 20 dB per decade. We've also seen that the phase is always 90 degrees for all frequencies. We can also look to the Nyquist plot and create the Nyquist plot. And then we see that the phase is always 90 degrees. So we have always points on the positive imaginary axis. And for increasing frequencies, we see that the amplitude goes up. So we start off in the origin and we are always on the positive imaginary axis. So my Nyquist plot looks like this. An increasing vector over here starting in the original and ending on the imaginary axis in the infinity, and so in infinity. All right, now let's look to a realization of a differentiator with op amps and RSNCs. Well, this RNC combination gives the differentiating action in the analog domain, and we can look also in the S domain by replacing j omega by s, and then we get the transfer function h is equal to s times ti. So again, we have an expression with an s, but we can also say this is s times ti over 1. And when we do that, we see that the denominator has no parts with s in it. So there are no poles. There are only zeros. And that 0, it's only 1 0 because there is only one s over here. It's not an s squared or s to the power of 3 function. So we have 1 0, which can be calculating by putting this expression to 0, which yields s is 0. So we have 0 in the origin. So in the PZ plane, in the S plane, we have a 0 in the origin. All right, that's the differentiator. Now let's look to the bias integrator, which is also known as the first order system. Well, this is the mathematical model. It says that the time constant of the system, Ti, times the derivative of the output plus the output equals the input. Well, there are lots of basic integrators in mechatronic systems. You can think in electronics, you can think of an RC network, but also a first order representation of a DC motor from input voltage to angular velocity equals a first order system description. So this is the mathematical model description in the time domain, the differential equation. When we go to the S domain, when we go to a transfer function, we replace ddt, the derivative, by s, and then we get ti times s times y plus y is equal to x. So you can say y times sorry, in the S domain, it equals y is equal to x divided by ti times s plus 1. Again, because when we cross multiply this, then we get y times ti times s, which is in the time domain this part of the differential equation, plus 1 times y, which is this part of the differential equation, and that equals s. So the transfer function y over x, which is defined as h, equals 1 over tau I times s plus 1. And tau I is the time constant of the system. And we can go directly to the j omega domain by replacing s in j omega, and then we get a transfer function over here, which is equal to 1 divided by 1 plus j omega times tau I. But for the Bode amplitude plot, we often we look to the amplitude in dBs, and we are going to look to the phase. So the amplitude of this transfer function is equal to 1 divided by the square root of the real part, which is 1. So 1 squared plus the imaginary part squared omega times tau I squared, which has been written over here. And for the Bode plot, we take 20 times the logarithmic function of this amplitude. And the phase is equal to the phase of the numerator minus the phase of the denominator. So the phase of the numerator is 0 because it is only a real number, which is always on the real axis. And the phase of the denominator is minus the arctangent of the imaginary part, omega times tau I divided by 1. So it's minus the arctangent of omega times ti, tau I. So knowing that, we are going to look into the specific frequencies again. We're going to look to omega is 0, omega is the infinite number, and omega is the crossover frequency, which is defined in this case by the frequency in which the real part of my transfer function over here is equal to the imaginary part of my transfer function. So omega times tau I equals 1, so omega equals 1 over tau I, that frequency. Well, at omega is 0, we see that the amplitude is 1 over 1, which is equal to 1, and it's in dBs 20 times to the log of 1, which is 0 dB. For infinite numbers, my amplitude goes to 0, it's 1 over an infinite number, and in dBs it's minus infinite dB. And exactly on my crossover frequency, also known as the cutoff frequency, we get 1 over the square root of 1 plus 1, which is equal to 0.5 times the square root of 2, which is in dBs 20 times the log of this expression, which is minus 3 dBs. For the phase, we see that the phase is equal to minus arctangent of omega times tau I. So for tau I is 0, we have 0 degrees. When omega goes to infinite, then we have the minus arctangent of an infinite number, which is minus 90 degrees. And exactly at the crossover frequency or cutoff frequency, we get minus the arctangent of 1 over tau I times tau I, which is minus arctangent of 1, which is minus 45 degrees. Well, when we know this, we can draw the Bode amplitude and the Bode phase plot. So the Bode amplitude plot is drawn over here, and the Bode phase plot is drawn over here, and we did that by Matlab. So we don't have the asymptotic description, but the Matlab plot over here. In this example, my tau is 0.5 seconds, so my crossover frequency is 1 over 0.5, which is equal to 2 radians per second, which is the angular frequency over here. In the amplitude plot, we see that for low frequencies, the amplitude is 0 dBs, and for high amplitudes, it goes to minus infinity, and exactly at the crossover frequency, that low frequency behavior changes into the high frequency behavior, and here my amplitude drops by 20 dBs per decade. The phase for low frequencies was 0 degrees, for high frequency minus 90 degrees, and we've seen that at the crossover frequency the phase is minus 45 degrees. Well, that's the Bode plot, and we can also draw the Nyquist plot. More information about the Nyquist plot can be derived, is explained, let's call it that way, in the video about Nyquist plots. But summarized, we can see that the amplitude for low frequencies, omega is 0, is 1 and the phase is 0. Can be seen also over here from the Bode plot. For high frequencies, we have seen that the amplitude goes to 0 and the phase goes to minus 90 degrees. And the Nyquist plot can be described as a half a circle, which has a plot description like in this figure. And this arrow shows how the Nyquist plot goes when I go from omega is 0 to omega is infinite. Okay, we can also look into realization with analog components, for instance an RC network, and then we see that, for instance, when we put a step on an RC network, so a step on a first order system, and that is really important, my time response, the output of that first order system, has a curve like this, an e-power curve, so to say, and exactly at 63% of the end value, exactly at that point, the time with respect to the start of my output signal equals my time constant tau over here. So in a graphical way, you can always look to the 63 percentage point of my output signal, and at that point the time related to the start time of the response equals the time constant. It's only valid when I put a step on the input. We can also look to the Laplace domain, and then we replace again j omega by s, and we get the transfer function, which is equal to 1 over s tau plus 1. Well, it's an expression with a numerator and a denominator. In the numerator, there's no s present, so there is no 0. There is an s in the denominator, so there is a pole. And we can calculate that pole by setting that denominator to 0, and then we get s times tau is plus 1 is 0, so s is minus 1 over tau. So we get in the s-plane, the pz plane, we get a pole over here on the negative real axis because it's a real value, but it's a negative value, and it's a pole over here, and as we know, poles are drawn by a cross. So it's here, and remember that indicates that my system is stable. Okay, the last one is the bias differentiator, and the bias differentiator has a mathematical model, differential equation, which says that the output signal is a time constant, tau d, times the derivative of the input plus the input, and the input signal is x. So y equals tau d times the derivative of x plus x. Well, in the S domain, from the differential equation to the S domain, we can replace S again, ddt again by S, and then we get tau times S times X, so tau times S times X plus X, which is this part of the expression, equals Y. And the transfer function can be calculated again by dividing Y over X, which we call H, the transfer function, which is equal to S tau d plus 1. Okay, directly going to the frequency domain can be done by replacing s by j omega, and then we get for a transfer function h, the transfer function, equals j omega times tau d plus 1. So for drawing the Bode characteristics, we are looking to the amplitude and to the phase. And the amplitude of this function, it's a complex number. It's the square root of the real part squared, which is 1, plus the imaginary part squared, which is omega times tau d squared, and then the square root out of it. And for the Bode amplitude plot, we again take the logarithmic function out of this expression, multiply it by 20. And the phase of this function is the arctangent of the imaginary part, omega tau d, divided by the real part 1. So the phase is the arctangent of omega times tau d. So again, we are looking to specific points. Omega is 0, omega is infinite, and omega is equal to the crossover frequency, in which the real part of my complex number over here equals the imaginary part. So omega times tau d equals 1, so omega equals 1 over tau d. That's the crossover or cutoff frequency. Well, at omega is 0, we see that the amplitude is the square root of 1, so in dBs it's 20 times the log of 1, which equals 0 dB. When omega goes to very high or infinite values, we get an infinite value over here. So 20 times the log of an infinite value is also an infinite value. And exactly at my crossover frequency, defined as 1 over tau d, we see that the amplitude is the square root of 1 plus 1, so it's the square root of 2, which is in dB 20 times the log of the square root of 2, which equals 3 dB. The phase is equal, we have seen it, to arctangent of omega times tau d. So when omega is 0, the phase is 0. When omega is an infinite number, we get the arctangent of an infinite number, which is 90 degrees. And exactly at the crossover frequency, we see that it's the arctangent of 1 over tau d times tau d. So it's the arctangent of 1, which equals 45 degrees. So now we get a Bode plot, which is almost the inverse of the Bode plot of the bias integrator. We start off for low frequencies at 0 dB, and then at the cutoff frequency we see that the amplitude is increasing, and it increases when we go back to this transfer function. We see that it increases by 20 dB per decade. So that happens from the crossover frequency, and in this example my time constant was 0.5 seconds, so my crossover frequency was 1 over 0.5, which is 2 radians per second. So again, at 2 radians per second, my low frequency behavior changes into the high frequency behavior, and we see that the Bode amplitude plot increases by 20 dB per decade. And remember, a decade is an increase in frequency by a factor of 10. Well, the phase plot starts off for low frequencies at 0 degrees. It ends up for high frequencies at 90 degrees, and exactly at the crossover frequency, we see that the phase is 45 degrees. Well, that is the Bode amplitude plot. The Nyquist plot is shown over here, and it can directly be derived from the transfer function which we have written over here. And that transfer function is nothing more than a complex number with 1 as a real part and the imaginary part omega times tau d. So for increasing frequencies, my real part is always 1 for all frequencies, and my imaginary part for increasing frequencies starts from 0 to an infinite value. So for the Nyquist plot, in which we have always on the horizontal axis the real part of the complex number and the imaginary part on the vertical axis, we see that we always have a real number of 1, and we have an increasing number on the imaginary axis. So my Nyquist plot starts off for omega 0 exactly in the point 1, and then it increases, and the Nyquist plot goes up like this. So the Bode amplitude plot is more or less, Bode plot amplitude and the phase plot is more or less the inverse of the Bode plot for a biased integrator, but the Nyquist plot is not the inverse of the Nyquist plot of a biased integrator. Remember that. Okay, last but not least, we're going to look into the pole zero plot, And then we've seen that the transfer function in the S domain is equal to h is s times tau d plus 1. So we can say, well, that is s times tau d plus 1 divided by 1. So in the numerator, there is an expression with s, which yields a 0. And in the denominator, there's no expression with s, so there's no pole. So the 0 can be calculated by setting s times tau d plus 1 to 0, which yields s is minus 1 over tau d. So we have 0 over here on the negative real axis over here and the S plot and the PZ plate. Well, that's all about first order systems. We've seen that, and that's an important thing, that for all first order systems we have an increase or decrease in the frequency domains when the Bode plot with 20 dB per decade plus 20 dB per decade for the differentiator and the bias differentiator, and minus 20 dB for the integrator and minus 20 dB per decade for the bias integrator. That's always important to notice when you look to Bode plots, because and that way you can see, well, there is a first order behavior in my system. Well, that's the first video. Thank you for watching, and I see you in the next video.